Alrighty, so let's go ahead and get started today. So, first of all, I just wanted to start with a reminder. I mean, this is on Canvas, it's in the syllabus, it hasn't changed, but just a heads up that the midterm is 2 weeks from today. So, again, that's Halloween. And if you look on Canvas and you go to modules and you click on the link for the midterm, you should see the topics, like the midterm topics, and also what my policy is during a test. I'll give you a hard copy of that next week, and I'll make some more comments. But if you want to, get like a head start, looking at what the topics are, and just kind of getting your mind in the frame that it's coming up 2 weeks, so you might want to start doing some preparation because you don't want to wait, of course, right until the night before. So there's quite a few topics. So anyway, I'll say more about it next week, but again, I just wanted to remind you. All right, so today the main topic is decoders, and a decoder is part of Lab 3. So last week, you were able to design the MUX. That's part of Lab 3. And then also the RCA is part of Lab 3 that you did in Lab 2. But like I said last week, you don't have to do anything to it. You can just bring it over into your Project 3. And once you know what a decoder is, and I'll explain how you'll model a decoder in Verilog, you'll have the last piece that you need to do Lab 3, which is taking those 3 modules and connecting them up in a certain way where the entire circuit will add, 2 binary numbers, 4-bit binary numbers, A and B, with the RCA. But then instead of displaying the result as binary on LEDs like you did in Lab 2, you'll display the result as a hex character on a 7-segment display. Okay? So that's one of the things we'll talk about is how the 7-segment displays work on your basis board. Okay, but the first thing I want to talk about before we get to decoders is another way that binary is used to represent numbers, and it's this BCD, which stands for binary coded decimal. Okay, and before I give you an example of binary coded decimal and also kind of explain why, what its purpose is, I just want to go back and review something, because once people know about BCD, they start to confuse it with something that we talked about earlier. So I want to go back to that something earlier just to kind of reinforce it before, I talk any more about BCD. So this is what I want to reinforce, okay? This is something we've talked about, right? This was on the first day, right? When we did number bases and base conversion. And remember how we talked about that you can go from hex to binary or binary to hex directly by grouping bits, right? Like you can do this without going through base 10, right? So do you remember, like, say you had this 1, 4, 5, 9, and base 16. Remember, this is a way that we can show the base, right, with a little subscript. Right? So if I wanted to go directly from this 1, 4, 5, 9, and base 16 to binary, what would I do?
You would have 4 bits for each digit, and then you just get the value in binary.
Exactly. So what would I write here for 9?
That would be 1001. Yeah.
Yeah. 1001. Because I just write the 4-bit binary group for that hex character. Right. So what would I write here?
0, 1.
0, 1. Right here. Again, that was fast.
0, 1.
Okay. It sounds like 0, 0. Okay, what would I write here? Now you could, but because there's 3 zeros, and yeah, you could just write 1. But technically, yeah, 4-bit. I mean, if you did write this, it's not valid. That would be right too. But as you know, zeros to the left aren't going to change values. You don't have to write it. Okay. So the key point here is that now, if you figured out, what this was in base 10, And if you figured out what this binary was in base 10, you would see that they're equal. Okay. Right, that this in base 16 is the same as, you know, what we wrote in binary. And then we can go the other way too, right? That we can go base 2 to hex by, you know, grouping in 4s. Right, again, here you just kind of imagine that there's 3 zeros here. Right, and then you write each 4-bit binary group as a hex character. So what would I write here? What would I write here? 11, which is B. B. Yeah, because sometimes I see people actually write 11, but you gotta put the character, right? In hex B, and then you just have 1. So you know, this in binary is equal to 1B3 and hex. And again, if you converted this to base 10, right, that the number what it was in base 10, you did the same thing here, you would see that they were equal. Okay, so you know, this is base conversion. Okay. Now what I'm going to show you is binary coded decimal to decimal. And when you're doing this, you are not doing base conversion. Okay, it's going to look a lot like when we do base conversion between binary and hexadecimal, but that's not what we're doing here. Okay, so binary coded decimal, it's not like a base. Okay, what binary coded decimal is, it's a subset of binary. Okay, it's binary. It's binary from 0, 0, 0, so it's also 4 bits. The 1, 0, 0, 1. Okay, so it's a subset of binary that goes from 0 all the way up to 9. Okay, and we use BCD to represent decimal digits. Okay, so if I wanted to take this base 10 number and show it as BCD, I would just take each digit and represent it as a 4-bit binary number. Okay, which is much like what we're doing here, but the big difference is this is not base conversion. Okay, so to take this decimal here and make it into BCD, I would just take each digit, write it as a 4-bit binary. Then I would put BCD. Okay, as a subscript to show that it's BCD. Okay, so you see what I did here? I just wrote the 1 as 4 bits, the 4 as 4 bits, the 5 is 4 bits, the 9 is 4 bits, right? Just like I did up here. But again, this is not base conversion. We're not saying that, you know, this is like a different base and they're equal. We're just saying this is another way to represent a multi-digit, or doesn't have to be multi-digit, it could be a single digit base 10 number as binary bits. Okay, I mean, what was the reason that we chose groups of 4 here when we did this base conversion from hex or binary? Yeah, it's 2 to the 4 is 16. 2 to the 4 is 16. See, that's why this base conversion works. See, here again, we're not doing base conversion because 2 to the 4 isn't 10. Okay, this is just another way to represent base 10 with bits. And the main reason binary coded decimal, you know, came about, like the purpose of it, is because of 7-segment displays that we're going to get to. Okay, so nobody's going to confuse BCD with base 16 because again, that's the common mistake people make.
So basically, it's just binaries with the display decimal.
Right, exactly. Yeah, I think once we talk about a 7-segment display, this I think will make sense. Yeah, or more sense, hopefully. Okay, so that's what BCD is all about. All right, so let's go on and now and talk about decoders. And I wrote the definition of a decoder up here. You know, the very general definition. A decoder just takes signals and converts those signals from one form to another. You know, we're talking about digital decoders in this class, but you know, there's analog decoders. There's lots of circuits that, take some signal and converts it into a different type of signal. I mean, half-wave rectifier does that, if you're familiar with the half-wave rectifier, full-wave rectifier. Okay. But as some examples, lab 3, the decoder that you're going to be building in lab 3 is going to take binary and convert it to hex. Okay, binary is going to go into your decoder, and then out of your decoder is going to come bits that drive a 7-segment display and shows that binary as a hex character. So it's essentially going to be doing this. Okay. Also in CP233, and I put the diagram of the microprocessor that you build in CP233 on the table. Again, please don't take that diagram with you. I'm going to use it in my other sections today, so you can just leave it on the table at the end. If you want to take a picture of it, you can. But if you look at that diagram, you'll see that over towards the upper right of the diagram, see where it says CUDCDR? That stands for Control Unit Decoder. Okay. Now, right above it is another block that has CUFSM. That stands for Control Unit Finite State Machine. And we're going to talk about finite state machines in a couple of weeks. Probably about 2.5 weeks from now. But if you take a look at the decoder, on the left side, which is the input side, up towards the top, you'll see like a little tag, little tag symbol, and it has IR, and then in square brackets says 14 to 12. What that stands for, the IR stands for instruction register. Okay, we're going to learn what registers are in a few weeks also. But the instruction is referring to a microprocessor instruction. And the 14 to 12, that's referring to 3 bits of that instruction. And then right below it is IR 30, so that's instruction register, the 30th bit. And then under that is something called, or short for interruptation, which doesn't really apply to what we're talking about here. But also, if you look up at the very top left, where there's a /7, it goes to IR and then in brackets 6 to 0. That's another 7 bits of the instruction register. The instructions in CP233 for the microprocessor you build is 32 bits. So this decoder, it's taking, 7 bits, 6 to 0, then it's taking another 3 bits, 14 to 12, then it's taking a single bit, the 30th bit. And that's what's going on the input side. And then on the output side of the decoder, there's ALU fun, ALU source A, ALU source B, PC source, RFWR select. Now you're going to learn all about, what those things mean when you take the class. But what I want to point out at this point is, look at where those outputs of the decoder are going to, like where they're connecting. Like where else do you see ALU fun? The diagram, you look. Yeah, it's by this thing called an ALU. How about ALU source A? Okay, MUX. How about ALU source B? By MUX. How about PC source? A MUX over on the left there. And how about RFWR select? Yeah, so you see, now what you'll learn when you take that class is that the ALU, which stands for Arithmetic Logic Unit, it ends up being modeled as a big MUX. Okay, so all those outputs of the decoder are going to MUXes, and specifically what input of the MUX? The select input. See, each of those 5 outputs is going to a select input of a MUX. And how does a MUX work again?
Switches with one.
Right. There's multiple inputs. Like if you look at each of the MUXes, the ALU has 2 inputs. And then the MUX that's got the select ALU source B, that's got 4 inputs. The source A MUX has 2 inputs. The PC source MUX has 6 inputs. The RFWR select MUX has 4 inputs. So you see what this decoder is doing, and the reason why it's called a decoder, is it's taking some of the bits of the instruction. It's not taking all 32, okay, but it's taking, about maybe 10 or so. It's taking some of the instruction bits and then taking those bits and converting it into select bits or muxes. And what the muxes are doing is routing the data through the microprocessor. So you see in CP233, the decoder is essentially taking an instruction and then making it happen. And the way it makes it happen is by routing the data, in the path that it needs to go for a particular instruction. When you take that class, you'll learn that there's like 60 different instructions. And depending on the particular instruction, the data has to flow through the circuit a certain way. And it's the decoder that's controlling. I mean, that's why it's called the control unit decoder. Okay? So, that's just a couple of examples. I mean, there's like an infinite number of examples of decoders. Okay? All right. So, the next thing to talk about, well, the next thing to do is to move the camera. So let me do that so I don't forget. I had a very hectic morning this morning because, first of all, my internet was down at my place, so I couldn't get on the internet this morning. And then I come here and my phone is giving me trouble now. I don't know what's wrong with my phone. It will only let me make emergency calls. I can't call anything else. So, has anyone ever had that happen to them? I have a Samsung Galaxy. Oh. Yeah, I did that. It seemed like it worked for a little bit, and then you take up this. I did not. Have you tried turning it off? Yeah, I did that. I restarted and then I did a closed boot. So I don't know. I'll have to figure it out afterward. I'm just trying to get onto my portal. I can't get onto the portal. Because that's one thing with the portal, right? Unless you have a phone, you can't get on. There's no other way. Like they won't email you a code. What's that? They have the Authenticator app. Okay, I don't have it. And I need my phone to get it. Yeah. So,
well, you don't need cell service for it. Connect to the school Wi-Fi to access the app.
Okay, I'll try that out. Yeah, thanks. That's a good idea. Okay, but anyway, back to this. So the 7-segment display on your Basis 3 board, you have 4 of them, and they're all identical. Okay, and it's called a 7-segment display because, lo and behold, there's 7 segments. Each segment is an LED. Okay? LED stands for light emitting diode. How many people have had some sort of like electronic? How many people know what a diode is? They at least have heard of a diode. Okay, just about everybody. There's a few people that didn't. Okay. Well, each one of these lines that I drew here represents a segment, which is an LED. And by convention, this is how we label it. Okay, this top segment is the A segment, then it goes B, C, D, E, F, and then the middle segment is G. Okay. Now, if you dealt with diodes at all, you probably know what AN is short for. What do you suppose AN is short for? Anode. Okay. So this type of display is called a common anode. Okay, the reason they say common is because all the anodes are connected together. And so again, for those of you that haven't dealt with diodes before, the symbol of an LED, which is the diode symbol, which is the arrow with the line. And then to identify it as an LED that gives off light, that's what the arrow represents. Okay, because there's diodes, of course, that don't give off light. But the LEDs that do give off light, their symbol just has the 2 arrows that indicate that. So, all the anodes are connected together. So that's why it's called common anode. And then each cathode is separate. So, the A, B, C, D, E, F, G over here, these are cathode inputs. Right, so all these are cathodes. Does anyone know what letter we use for cathode? K. Yeah, we use K. We don't use C. Why don't we use C? Yeah, capacitors. Yeah, cathode we use K, even though it's spelled. Okay, so, you know, each segment is an LED. Now, what is this the symbol of? Not here. Okay, I'll come back to that in just a second. But first of all, for the next thing is this. Right middle. I gotta move the camera a little bit. So I get it. So this is out of range here. So over here, just a little circuits review. I mean, for people that have had circuits. Again, if you haven't had circuits, don't worry. This isn't testable. People that have had circuits, this might help understand how these 7-segment displays. Okay, so in circuits, very simple. This is probably one of the first days you learn about this. Say you have a resistor. And you want the current now, you know, assume the current is positive charge flow, right? You all learn that in engineering, we think of current as being movement of positive charge, where physicists, you know, they look at the electron flow, but we look at positive charge flow. So if this is positive charge flow, right? I want the current to flow this way through the resistor. What's the polarity of the voltage going to be? Like, where's the higher end of the voltage going to be, and where's the lower end of the voltage going to be? Yeah, be like this, right? Because as current flows through a resistor, you get a voltage drop, right? So as current flows, you're going from a higher voltage to a lower drop. And do resistors ever supply power? No, they only absorb power, right? Anytime you get a voltage drop, that's absorption power, right? In order to supply power, you'd have to have a voltage rise, right? Current would have to go from the lower end voltage to the higher end, right? Okay. Well, diodes and LEDs, like resistors, can only absorb power. They can't supply power. And current through an LED will only flow anode to cathode. Okay. So to get current to flow through a diode, the anode has to be a higher voltage than the cathode. Okay. The way diodes are constructed is that if you try to get current to flow cathode to anode, ideally it won't happen. Okay, ideally, you get zero current if you try to get current to flow cathode to anode. Now, in reality, you get a smaller current. But to get appreciable current, you got to have the diode bias like this. It's called forward bias. I'd have heard that term. Okay. Okay, so just a little review here. So based on this little review, what do I want the common anode to be? Do I want it to be a 1 or a 0? Because remember, 1 means plus voltage, 0 means ground, 0 volts. Yeah, I want this to be a 1. Right? Because that's going to put positive voltage on the anode. And now if I make a cathode a 0, right, ground, I got 5 volts on one side, I got 0 on the other side, current's going to flow anode to cathode. And when you have an LED that's forward biased where current's flowing through, it's going to give off light. Okay. But if I put, so this would be lit. Okay, if I have a 1 on my common anode and I make the cathode of segment A a 0, that segment would light. It would be lit. But if I made cathode B here, okay, the cathode of the B segment, if I made that a 1, well, now I got 5 volts on each side. Right, so equal voltage on equal side of something. Is any current going to flow if you don't have a potential difference? No. So you see, this segment would be off. Okay, so wherever you have a 0 on the cathode, that segment's going to light. Wherever you have a 1 on the cathode, that segment's not going to light. Okay, so you see, by properly putting 0s and 1s on the cathode, I can make different numbers and characters on my display. Let me just say one more thing. I'll get to your question. Now, the only other thing is this NOT gate. The way the basis board is constructed, and I forgot to mention, but I put this handout. Now, there's enough of these for everyone. There should be anyway. My intention was to have one of these for everyone, but there's also some important information on the back of this. But on this side of this handout, talked a lot about what I'm going over right now about the 7-segment display. And this page came out of a reference manual for the Basis 3 board. And that reference manual is on Canvas. I posted it on Canvas. I only show this page in class, but at some point, someday when you're bored and you're looking for something to do, you should take a look at that reference manual. There's all kinds of neat stuff. And see, the reason for this NOT gate is, remember, this was a couple of weeks ago when we were talking about logic gates, like the ands and the ors. And I showed you that one example of a electronic circuit that was a NAND gate, right? And it had like a transistor and it had a couple of diodes and a couple of resistors. Well, you can make an inverter, a NOT gate, with a single transistor. So that single transistor is what's giving the inversion. And the reason why they put an inverter here, instead of just having the anode go directly to the connection here, they put this NOT gate, which is a transistor, is because they want to get some current gain. Okay, the transistor wasn't here, the LEDs wouldn't have enough current. There wouldn't be enough current for the LEDs to get it to be bright enough. Okay, so the NOT gate is there is just, to get a better illumination of the LEDs. So because the NOT gate's here, this input, this pin here of the 7-segment display, well, that's going to be a 0 in order to get a 1 on the side where the anodes of the LEDs are. Okay. Now, I just drew one 7-segment display, but for all the 7-segment displays that are on the Basis board, it's all the same. They're all connected the same. They each have their own anode and they each have their own cathode. Okay, so, say this is the furthest to the right, like when you're looking at your Basis board with the switches on the bottom, the furthest to the right 7-segment display, that's like the 0th display. So this would be like A0, this would be like seg A0, seg B0, and so on. And then to the left of that, that display is the first display. So you'd have like AN1, and these would all be seg A1, seg AB1, and so on. And then, you got display 2 and you got display 3. Okay, so because there's 4 displays, you got 4 anode inputs, and you also have 4 sets of cathode inputs. Does that make sense? Okay. You had a question earlier. It was about the NOT gate. Oh, okay. Yeah. All right. Yeah. Okay, so while I don't think it's like absolutely necessary that like the innards of how the display works. I mean, really, if all you knew is that you have to make this a 0 and you got to make cathode 0 in order to get a segment to light, that would probably be good enough. But I just felt like, at least for some people, it would be helpful to know some of the details, especially if you had circuits, because again, it ties into stuff that you've learned in other classes. Okay. All right. So any question on the 7-segment display before we move on? Because now we're going to talk about how to actually make a decoder that's going to take binary information and then display it as data on a 7-segment display, specifically hex data. Okay. All right. So, I mean, where you would start is with the truth table. And here is the lab 3 schematic. And right here is the decoder. You can see it, calling it a binary to hex, binary to hex decoder. So this decoder, it's got a 4-bit input, because we're taking the 4 bits coming from the sum output of your RCA, right? Remember the RCA from lab 2? So we're going to take that sum. That's where the result of the addition is, right? And that's what we're going to feed into the decoder. So if I want to fill out this truth table, since there's 4 bits, how many rows of this truth table am I going to have? 16, right? So you see here I have all zeros, 0, 0, 0, 1, 0, 0, 1, right? Just fill it all out. You've done this before, right? go in binary order. If I make a mistake, let me know. 2, 4, 6. One, 0, 0. Get them right. 2, 4, 6, 8, 10, 12, 14, 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Like I said, it's always good to double check. It's easy to make mistakes. All right, so now in the next column, we're going to put what the 7-segment display should look like. Okay, so if I've got all zeros, well, I want a 0 to show up on my 7-segment display. So that means I want the A segment lit, the B segment lit, the C segment, the D, the E, and the F, right? The only segment I don't want lit to show a 0 is the middle one, that G, right? To show a 1, I just want the B and C to be lit. Show a 2, that would be these segments. And you could keep going, right? 3, 4, 5, 6. Okay, so 3, 4, 5, 6, 7, 8, 9. Now, what are we going to show? Since we want it to be a binary to hex, what are we going to show when there's a binary 10 at the input? Right. And make it a capital A. Right, so everything's going to be lit except for the D segment. Okay, now we get to 11. So what are we going to do for 11?
Lowercase b.
Yeah, why lowercase b?
Because otherwise it looks like an 8.
Exactly, right? Yeah, that makes sense to everybody that because of the limitation of the display, there's only 7 segments. If I show B as a capital B, it's going to look just like an 8, right? So for B, you would make it a small case B. All right, and then we'd have what after that? And what?
Lowercase p.
All right, yeah, why lowercase d?
So that it looks like 0.
Yeah, it look like it's 0, right? So that would be lowercase d. Oops. And then you got Ian, right? Okay, so that's what, you can fill out the blanks. Okay, and do all of it, but if you follow what we did, I think you can do the rest, right? Okay, but now the next thing is, okay, well, what do we have to make these cathodes in order to get this 0 to light, right? Again, the anode, the common anode has to be a 1, but input AN has to be a 0, again, because of the inverter here. So what do we have to make the cathodes of the segments that we want lit equal to? 0. So what would I write here to get a 0 to show up? And see, this is the G, these are cathodes. Why are they metals? These are the cathodes. Yeah, does everybody see? It would be 1 and then 6 zeros, right? Because I want all these segments to light. I want A, B, C, D, E, F. I want all those to light. The only one I don't want to light is G. So I make that one a 1, right? Because that would put equal voltage on each side of this LED, and therefore no current, therefore no light.
So you selectively apply voltage to keep a light off.
Right, yeah, in this case, yeah. Yeah, this is, you would make the cathode like 5 volts. And that's because on the other side is 5 volts. So again, you'd have equal volts and no current. Okay, how about for the 1? What would I want to do there?
All 1s except for C and D.
Yeah, right. I only want to light segments B and C. So those would be the only 2 that I would have as a 0. These 2. The rest would be all 1. Right? Because all the other segments I want on. All right, and you would do that for all the characters. Right? Does anyone want to see another one, or do you get the idea? Okay, all right. Now, the next thing here, this next step isn't like it's not something really necessary, but it's something good to do because it will help you when you go to verify that the one you build in System Verilog is working the way you want it to work. And that's to show these 7 bits of the cathode bits here. Instead of showing it as binary, ones and zeros, to show this as hex. So if I want to show 1 0 0 0 0 0 0 in binary as hex, how can I do it quickly without going through base 10? You did it at the beginning of your class. Yeah, the grouping, right? Would be 8 0
4 0.
4 0. Yeah, it's 0 here, and then remember this would be 1 and 3 4. So this would be 40 hex. Okay, what would this one be? 79 hex. All right, so you see, you're getting some review of things we talked about earlier. And again, this shows you why hex is a popular base in digital, because instead of saying 1 0 0 0 0 0, I can just say 40 hex. Instead of saying 1 1 1 1 0 0 1, I can say 79 hex. And then when you go to verify on the timing diagram of your System Verilog to make sure this is working, because when you build this decoder in Verilog, which you'll be able to, to do today, once we're done here, you're done with the activity. How many test cases are you going to have for your decoder? 16, because you need this whole truth table. And I think at least some people missed, based on some emails and also some comments I saw from the graders for various labs that have been graded. Not all this section, I have 2 other sections, so I'm not saying everyone in here, but there, I think, are some students that in my intro to Vivado video, I think you missed the part where I show that you can change the base of what you're looking at for the timing diagram. So like when you look at the timing diagram for this decoder, instead of looking at it in binary, which I think is what it defaults to, you can just change the base to hex. And then you can just verify by looking at, that the hex is correct for that test case. Okay, so I'm going to let you fill out the rest of the table, but you need to fill out this table before you build your decoder in Verilog. Okay, because once you have this table, building it in Verilog is going to be pretty cookbook, as you're going to see coming up. Okay, but before, in fact, that's the next thing. Before I show you how to model the 7-segment display decoder in Verilog, do you have any questions up to this point? Okay. So are you all confident that you can fill out this truth table?
Do you want to see uppercase or lowercase?
For the letters, yeah, all uppercase except for the ones that you can't. So yeah, make this like an uppercase C. Uppercase C. And have an uppercase E. Uppercase F. Okay, so everybody confident that, especially this, everyone sees how you go from binary. Again, we talked about that on the first day, right? So this is just some review. You can figure out what the cathode values are, right? You just want a 0 for whatever segment you want lit. Okay. And this is another example of, zeros and ones in of themselves are just voltage levels, right? What gives them meaning is the circuitry you build around them. So it's it's this decoder circuit that's giving the bits the meaning of a hex character now, instead of binary like we had coming out of the RCA. All righty, so now let's see, am I still in view over here? So I turn this a little bit. Yeah, somebody over the weekend played with my camera. They moved the settings. I don't know why anyone would do that. What joy does that give anyone? I don't know. I know.
Sometimes I wonder if we asked it all about each other. We're all doing the same. We're like, why would you do that?
Okay. All right, so last class when we talked about a mux, I showed you, and you're expected to do the same, to model the mux with an if statement, right? How many people actually have a working mux? They get it working mux. Okay, not everyone, but a lot of people. Okay, so if you haven't done that, that's where you start today. You want to get your mux working first, and you have to use an if statement for the mux. Okay. For the decoder, we want you to use a case statement. Now, let me be clear. You can do a mux with a case statement, and you could do a decoder with an if statement. But the reason we want you to do the if statement with the mux and the case statement with the decoder is we want you to get practice with each. Okay, so that's the reason. So please follow the instructions. Sometimes people, they fall in love with one of them. They do everything in if statements, or they do everything in case statements. But when you get the CP233, there's reasons why you would want to use one or the other, and you need to know both for CP233. So, okay. So anyway, like any module, you give it a name. Now, I'm not positive, but I think if you start like a file name with a number in Verilog, System Verilog, it doesn't like it. So don't do like 7seg like that. You got to spell it out. Okay, I don't think it likes names with numbers at the very beginning. I think you put numbers later on, but not at the very beginning. So that's why I have it spelled out here. So you would declare your inputs and outputs just like you've done before. So here again, this is our module. So this is like our high level, if you will, for the decoder. So there's only one main input, there's only one main output. Okay, 4 bits, 7 bits, right? You need 7 bits because there's 7 segments. Okay. Let's see what I was going to say. Okay. So you declare your inputs and outputs, and then just like with an if statement, a case statement has to go in or within an always comb block. All right. So after you declare your inputs and outputs, you have always underscore COMB, and then you would need your begin. Okay. Now, just like last time when we said, any output that's within an always comb, now there was an if statement, here it's going to be a case statement, but the same is true. Anytime you have an output within an always comb, you've got to put logic between output and the name of the output. So, when you declare your output for seg, it's got to be output and then logic and then 7 to 0, seg.
7 to 0, 6 to 0.
6 to 0, sorry. Thank you for correcting. Yeah, later on you'll see in a lab, I'm not sure if it's lab 4 or lab 5, but you'll see that we eventually will have to make that leap. But yeah, it's 7 now, so it should be 6 to 0. Yeah, thank you. Yeah, you definitely get in her. Okay, so you got your always comb and then your begin. So for a case statement, you just put case, and then in parentheses goes what's called the sensitivity list. And what's meant by sensitivity list is whatever you put within the parentheses, when that changes, that's when the case statement's evaluated. So we want the case statement to be evaluated anytime this input changes, this DIN. So you see, that's what would go inside the parentheses, right? Because whenever this data, this binary data going in changes, that's when we want to change what the output is. Okay, so that's why that's in the sensitivity list. Okay. All right, and then you just put 0 for the, the first case here. It always starts with 0. So our first case is going to be, we want our seg output to equal 7, tick mark B, and then we just put the bits. So 1, 0, 0, 0, 0, 0, 0. Let's see, is that right? That's 6 zeros. And then semicolon. Now, you could also, instead of doing 7 tick mark B and then listing the 7 bits, you could also do 7 tick mark H and then put 40. All right, so you could put this in hex if you wanted to. But if you do that, it's still got to be a 7. That's one thing that threw me off with Verilog and System Verilog, is that I thought because it's 2 hex characters, it would be like 2 tick mark H40, but when you do that, you get an error. So like in CP233, where you got 32 bits, right? If you do it in hex, you still got to put 32 tick mark H, and then you put like 8 characters there. 32, and each character is 4 bits. So, all right. But anyway, you can just list out the bits. In fact, maybe from a learning point of view, it's good to list it out as bits, just so it drives home that each cathode has a bit value. But then you just basically take what you have on the truth table and just translate it into this case statement. So, for case 1, which is, this row here, we want seg equal to 7 tick mark B 1 1 1 1 0 0 1 semicolon. Right, and you just do that for the whole truth table. You have to go 2, all the way down to 15. Okay, and these are in base 10. The options, you just put the base 10 number. Okay, so any questions that, again, you can fill in the rest, right? It's just from the truth table.
So does System Verilog automatically translate the input into base 10 for you?
The input into base 10.
Because we have an input of 4 binary bits, and then our cases are all.
Well, I think it just, in a case statement in System Verilog, it just, whatever number you put here on the left side of this colon, it just takes its base 10.
Okay.
And then you got to tell it, what the output is equal to for that option. And then you can tell it the base here. Yeah. But I don't think, are you asking if you can change this base?
No, I'm saying because doesn't it read in bin and then pick from one of those cases? So does it automatically turn bin into base 10?
Oh, okay. Yeah, it must. Yeah, it must somehow take this and translate it. Yeah, but it does that internally. Like you don't have to tell it to do that. Yeah, that's a good point. Okay, now also in a case statement, after your last option, you need to put a default. So after the last option here, you would write default semi or a colon, and then you would just set seg to something. I don't know. I set them all to 1 just to shut off the displays up, or all the segments up. But you can make the default whatever you want. Okay, and the default is there in case something happens where, for some reason, I guess, real life example would be, like say this system was on a satellite or something, and the satellite got blasted by solar flares, and there was like photons that changed bits. And, there's a situation where it got, that if you didn't have the default, it would get hung up somewhere in the case statement. So it's there for catastrophic, catastrophic case, so it doesn't get.
I say that on my Facebook, I've been talking about sport players.
Yeah, I was done too long. Where you faced this forward.
So what happened? You don't need to just explode.
I am so well. It could be depending on your computer. No, but actually, I'm glad you asked that because there was something last class that I meant to mention that I didn't, and I wasn't too worried about it because it's going to come up again. But in a case statement, if you don't have a default, it's gonna create a latch. That word, that ugly word we've been saying that if that's in a warning, treat it like an error. Again, a latch is a memory circuit. Okay, we're going to get to it in a couple of weeks. So if you don't have a default, it's going to put what's called an unintended latch into your circuit. Now, as I said previously, in this class, because the designs are not that complex, compared to that microprocessor, right? This isn't anywhere near the complexity. Well, having an unintended latch, memory, which is like additional circuitry, probably isn't going to affect the operation. It's probably still going to work because there's nothing time critical in this type of circuit. But the reason we don't want you to the reason we want you to treat errors that have the word latch or the warnings that have the word latch like errors is because in CP233, if you have unintended latches that add additional circuitry to that microprocessor, it's going to throw the timing off and your microprocessor is not going to work. Okay, so that's if you leave a default out. Now, the thing I didn't mention last class when we were talking about if statements, with building the mux with an if statement and if statements in general, is that your if statement, you need an if, and you can have as many else ifs if you want, or you don't have to have any, right? So else ifs are kind of optional, right? Wild card kind of thing. And then there's the else. Well, in an if statement, if you don't have an else, it creates a latch. Okay, that's the thing I forgot to mention last class. But the reason I wasn't worried about it is because one of the ways, in fact, the most common way that we create a latch when we want one, right, which we will want in a few weeks when we talk about memory, is you do an if statement without an else. So you see there, you're leaving the else out on purpose because it's creating memory, which is what you want. Okay, but right now we don't want memory because everything is combinational. Remember, COMB stands for combinational, and combinational is logic circuitry that doesn't have memory, so therefore it doesn't have latches. So you don't want latches. Okay. And then you would have to end the begin up here. So you would need an end. Okay, this end goes with that begin, and then you would end module. Okay, so let's see, we're at the top of the hour. It's not going to take me that much longer to finish, probably like 10 minutes. So you want me to keep going that way? Once I'm finished, you can start working. And does anyone want to take a break? No break? Okay. All right, so let's talk about lab 3. Now you have all the information that you need to complete lab 3. And here is the circuit for lab 3. And this is its purpose. Okay. Lab 3, this circuit, I call it adder hex converter. You can call it whatever you want. But it adds A and B and displays the result on the furthest to the right 7-segment display if the result is less than or equal to 15. If the result is greater than 15, does not display the result, and all 7-segment displays are blank. They're all off. Okay, so you got an RCA, and that's the same RCA that you built in lab 2, right? So like I said last class, have a separate project for lab 3. Hopefully, again, you've got separate projects for all the labs, and just bring over, okay, so in your design source window, you would bring over RCA design source, and also you'll need the full adder design source and the half adder design source, right? But you already have that, so you don't have, all you have to do is bring that over from your previous projects, right? It's no added work. You don't have to sim it, right? Because you already simulate, well, yeah, the assumption is that you've already have a good simulation with your RCA, otherwise your lab 2 wouldn't have worked.
Should all of the names work and stuff, or maybe I have to rename stuff?
You don't have to rename. I would just leave it all the same and use the same name. Yeah. The thing with Vivado is that if you start renaming stuff like afterwards, it can somehow screw it up where it can't find it any longer. So yeah, usually to rename something, you have to delete what you have and do the whole copy paste thing, whatever you name. So, yeah, try to avoid renaming. No, all you need are the design sources. Yeah, just those 3 design sources. Yeah, because like I said, you've already simulated it, right? You know it works. So, yeah. All right. Okay, now, if you've already designed your mux and you've tested it out, you're going to have your mux. Now you'll need, a sim file for that, right? Yeah, I'll test that. Okay, then you're going to have to build this, right? So you're going to have a design source in X, let's say, and you'll need a sim file for that. And how many test cases again for the decoder? Yeah, 16. You just got to make sure it's doing this truth table. Okay. All right, so see these design sources, sim files, you know, that covers all these, right? But what do you got left?
Constraint.
Well, yeah, there's constraints, but you need another design source and another sim file for what?
Like, healthcare.
Yeah, the whole thing, right? Because just like when you built the RCA, right, you had the half adders and full adders, right, the lower levels, and then you had the RCA, the top module, right, the structural model that connected it all together. So you're going to need, I ran out of space here, but I'll put it up here. You're going to need, you know, maybe you call it, you know, adder underscore hex converter HC or something like that. And you'll need the sim file that goes with that. Okay, so this is the one, you know, this is what connects everything together. Right, it's going to connect all this into the larger circuit. Now, I intentionally left out two things that you need to connect this all together. Do you know what they are?
Yeah, we need the T something.
Yeah, what do we call, remember in the RCA, I label them T1, T2, T3,
Yeah.
but you can label them whatever you want. But what are they in Verilog? We call them what? Starts with an I, 2 words, first word. Internal signals.
Yeah.
Internal signals. So yeah, you need like a T1 here and a T2 or whatever you want to call them. You know, to be more descriptive, you could, instead of using like T2 here, you could do like C0 select, right? Because this is connecting carry out of the RCA to the select of this mux. And, you know, you could call this like S underscore B or some underscore bin or something, you know, you can be more descriptive.
So where we normally in like the UEC would really assign variables to each other, can we just put in a bit value for the block?
Okay, so you're talking about the sim file for this overall circuit?
It will, you just have like four dot.
Oh, this down here?
Yeah.
Oh, I'm gonna get to that.
Okay.
Yeah, it's a good question, but yeah, I'm gonna get to that in just a second. Okay, but I just wanted to emphasize you know, these internal signals, because remember, in Verilog, when you're connecting lower level modules together, see how this lower level output's going to this lower level input? That's when you need an internal signal. When you're connecting lower level inputs or outputs to higher level inputs or outputs, you don't need an internal signal. So that's why you don't see any T1, T2 over here or over here, because we're connecting lower level to high level, right? Outside the box are the higher levels for the overall circuit. In fact, for your high level black box diagram, what am I going to write on the input side over here?
Orbit A.
Yeah, just the two binary that we're adding together, right? Right, these are the higher level inputs. And then what am I going to write on the output side?
7-bit seg, orbit A.
Right, exactly. And then say, remember the high level black box diagram, that gives you your main inputs, your main output. You're talking carry. Yep, right here, carry out. Okay, so now, well, any more questions? Oh, the other thing is, because the internal signals for the RCA were all a single bit, right? When you declare your internal signals, and remember the way you do that is after you declare the inputs and outputs for the overall, right, structural model, then you do logic, right? You define your internal signals with logic. Okay, well, what's different about this internal signal? It's 4 bits. Yeah, it's 4 bits. So you'll have to do like the 3 to 0, whatever you call this. Okay. It's just like when you have multiple bit inputs and outputs, when you have multiple bit internal signals, you got to tell the software, you got to tell it multiple bit. Okay, that's a common mistake is people will just put their internal signals as a single bit. And then of course the overall thing doesn't work. Okay. All right. So now Let's see how this circuit makes this happen. See, the way this circuit is connected, it's going to add A and B and only display the result when the result's less than or equal to 15. Otherwise, it's going to blank the display if the result is greater than 15. So, you all know what the RCA does, right? It's just going to add these two together, show the 4-bit sum here, the carry out here. So, when does the carry out of this RCA, when does it change from a 0 to a 1?
But when it gets higher,
Right, exactly. When the addition result is 15 or less, the carry out is going to be 0, right? It's only when the addition result is greater than 15 that the carry out will be 1. Okay, and look, the carry out is attached to the select of this mux, and then look at the input of the mux, the inputs of the mux. The 0 input. Now, by the way, one other thing I want to mention is, I'm not sure, because I've never done it, I'm not sure if you can name an input a number, like 0 to 1. You can try it. I wrote 0 to 1 here just for simplicity. When I did this, I actually spelled out 0, like ZER 0, 1. Okay, it might work with a number. I'm not sure though. Again, I know it works if you just spell out the name, of course. But you see here, the 0 input of the mux is connected to this 4-bit data, 1, 1, 1, 0. And this input 1 is connected to 4 bits all equal to 1. And then look where the output of the mux goes. It goes to AN. What's AN again? Anode. Right? It's this bit right here. So what is that anode controlling? Say it again.
7 segments.
Right, it's the common anode of the 7-segment display. So what does this anode bit have to be for there to be any chance for a segment to light? Well, this side of it, though. Okay, this side of it has to be a 0 to make this side a 1 for there to be any chance for a segment to light, correct? If the AN is a 1, and then this common anode connection becomes a 0, is there any way I could light a segment? Yeah, I can't light it. So you see, one way to think of this anode output to the 7-segment display is that it controls whether the display is going to light at all. Right? Where the seg bits determine which segment lights as long as the display has the ability to light. You have a question? The reason that the AN is 4 bits is because there's 4 7-segment displays on your basis board. So, the further when you look at your basis board and the switches around the bottom, the furthest to the right 7-segment display, that's like the 0th display. And then the next display is like the first display, then second display, third display. So, you have an AN0 for the furthest to the right display, an AN1 for the next one to the left, an AN2, AN3. Okay?
So are you using the carry out bit to just shut it off entirely, but don't have the clock to flop back and forth?
You said clock.
To flop back and forth, lighting up the 2 different anodes.
But before that, did you say clock, like the word clock?
Yes.
Okay, so you know what a clock is, because we haven't talked about that, but like a clock signal is like this. Okay, yeah. For that's another distinction between combinational circuitry and sequential circuitry. Combinational circuitry, what we're dealing with right here, has no clock signal. You're going to see when we get the sequential circuits, which have memory, you need a clock. Okay, so yeah, there's no clock here. Now, what was the other part of your comment that you made?
Just so, because you need the clock to swap back and forth between the 2 different.
Well, not clock, but the carry out.
The carry out, shut it off. So, because if you add a clock, it gets swapped back with different.
Okay, well, let's talk. I mean, you're right where I want to talk about next. So yeah, let's talk about it. We said earlier that if the result is 15 or less, this carry out is going to be 0, right? And if the result is greater than 15, this carry out is going to be 1. So let's say the result is less than 15, and this carry out is a 0. And that's going to put a 0 on the select. So with a 0 on the select of the mux, what is this output going to be? Which of these two is it going to be if there's a 0 on the select?
0.
It's going to be what's connected to input 0, which is 1, 1, 1, 0. So you see this 0 here, that's going to become AN, the 0th bit, right? And then the rest of these, you know, AN, the first bit, AN, the second bit, AN, the third bit. So that means my furthest to the right display is going to get a 0, which is going to make the other side a 1. The other 3 displays, they're going to get 1s, which is going to make the common anode part a 0. So what does that mean? What am I going to see on my basis board when we have 1, 1, 1, 0 going to the anode of the 7-segment display?
From the power.
Yeah, the furthest to the right. See, if I had 0, 1, 1, 1, like if I had reversed this, then the 7-segment furthest to the left would light. Okay, but we want the one furthest to the right. So that's why this is a 0. Okay, now when the carryout is a 1, meaning the result was greater than 15, what's going to be at the output here? All 1s. And if you got all 1s in your anode of all your displays, that's going to make this side of the NOT gate a 0. That's going to shut off all your displays. Right? So do you see how using the carry as a select to the mux, you see how it accomplishes this, where we blank the displays if the result is greater than 15, but we can show a display if the result's 15 or less. And if the result is 15 or less, well, now that's when the seg output matters, right? Because now, depending on what our seg bits are, that's going to determine what's displayed on that furthest to the right 7-segment display. Okay, so do you see how this diagram's connected gives us what we're looking for here? Now, the question that was asked a little while ago about, like, how would you actually code this? Like, how would you code having this data? You know, this 1, 1, 1, 0 at this input, and this all 1s at this input. Well, you do that in your top module, your structural model. You know, when you're making all the connections between the modules, well, right here, right, to make this connection, so this would be in this design source right here, your structural model. So in the line for that, you know, for the mux, like you would have mux, right? Because remember how we talked about last week, the first thing is the file name. Right, so if you want to make the connections for this mux, you start with the file name, then there's a label, you know, maybe you just call it mux 0 since there's only one mux. And then you start making the connection. So if you want to make this connection, let's see, it's parentheses, you would just go .0. Now, like I said, I don't think you can use numbers, so, you know, spell it out instead of just putting a number. But you put .0, and then in parentheses, you put 4 tick mark B 1, 1, 1, 0. Okay, so that's how you make connections to data, is you just put whatever input you want to connect to the data, then in the parentheses, you put the data. Now, some people, what they do sometimes is they make this connection in the mux module, like they'll do it in the mux module, but the reason I don't like that is because then if you go to use this module, this mux module in another design, you got to edit this. Right? If you make the connections to data in the structural model, you can just keep your mux just general, right? It's like when you designed your mux, you just made it output equals whatever you call this input, right? Like you didn't connect it to specific data in your design source. And that's the best way to do it, is make your lower level modules general, and then anything specific, like, you know, specific amount of data that you want to connect to an input, you just do it in the top. Okay, where you make all your other connections. Okay, that's sort of like standard practice. Okay, let's see. Do you have any other questions? Are you all confident that at least you know the process, right? Because again, if you haven't done the mux, that's where you want to start. Bringing this over from lab 2, that should take you all of 5 seconds. And then after you're done with the mux and you have it simulated correctly, you want to do the decoder. Once you have that simulated correctly, then you do the overall, the structural model, connecting everything up. And then you got to test that. Now, when you go to test your overall, right? And again, that's what you show on your demo that you submit, right? It's the overall design. And that's what the test cases are that are on Canvas. Again, that same file, that same Word document that has, the lab 2 test cases, it also has the lab 3 test cases. And lab 3 test cases are the same 10 test cases as lab 2. Okay, because you want to still make sure that your RCA is still working the way it should. But in addition, okay, that's not all. Okay, you do the same 10 test cases as lab 2. Okay, with additional test cases. Make sure all text characters are shown. Make sure all are shown, right? Because when you go through the 10 test cases from lab 2, it's not going to show, all 16 of these. It's probably only going to show about 10. So you got to make sure that in your video, you cover test cases so, like F is shown and E is shown and so on. Right? Now you can see I didn't put a specific number because there's different ways to do it. I think the best way to do it, so you don't miss any, is to do the 10 for the RCA, just repeat what you did for lab 2, and then just set one of your inputs to 0, like set A to 0, and just take B and go 0, 1, 2, 3, 4, 5, 6, right up to 15, and just show that, you're seeing, or show the grader that all these are being shown, right? Because we got to make sure, you use the lowercase b and not an uppercase, right? Because then you got 2 8s instead of a 8 and a b. Yeah. Okay. All right. So any questions? Because this is lab 3, the last thing, and I don't want to take up too much time because I want you to think about this during the activity. The activity today, I would say, now not to say all the activities, you had to think. I'm not saying like all the other activities you didn't have to think. But this one required, I think, a little higher level maybe of thinking. So that's why I think it's good that you're in groups where they basically give you a word problem, okay? It says design a logic circuit using an RCA, a MUX, and one logic gate. And you got to figure out which gate it is that does the following. So, I didn't make up this lab. It was either Dr. Benson or Dr. Mealy. I'm not quite sure who. But whoever made up this lab, they had to have like a thought in their head where they said, okay, I want to do a circuit where this happens. And then once they knew what kind of circuit they wanted, they had to then say, okay, well, what modules do I need? How do they have to be connected? So that's what I'm asking you to do. I'm asking you, like, if you were going to design a different lab where you're going to use one RCA, one MUX, and one logic gate, again, you got to figure out what gate it is, to do the following. Adds 2 4-bit binary numbers, A and B, and outputs a single bit, right? So, you should write like a high-level black box diagram, just like I did here, put your 2 inputs, put your output. Okay, then it says the single bit output indicates whether the summation of A and B is even or odd if the summation is greater than 15. Okay, and it will output a 1 if it's odd and a 0 if it's even. Okay, so that's one part of it. The other part of it is if the summation of A and B is 15 or less, the single bit output indicates whether input A is divisible by 4. Okay, single bit output equals 1 if A is divisible by 4, 0 if A is not divisible by 4. Okay, so that's the problem, if you will. So you want to come up with a diagram like this that will make this happen. Now, as a hint, I would write out, 4-bit numbers from 0 all the way to 31, right? This would represent your possible outputs of your RCA, right? Because here, you know, the carry out is 0, that's why you always see 4 bits. But then once it gets to 16, right, your carry out would be 1, and it would just go from 1 to 30. So I would write out all your possible outputs of your RCA, right? The sum and the carry out together. And then look for patterns. You know, look at every even number and look at every odd number. And see if you can see a way that you can easily distinguish between the two by looking for, you know, at a bit or bits. And then do the same thing for numbers that are divisible by 4. You know, like look at 4, look at 8, look at 12, and so on. And see if you can see a pattern. Okay, and that should help you come up with the diagram that you need.
Can we consider 0 divisible by 4?
I wouldn't, but I would consider 0 to be even. Okay, so anyway, work on that. Just like you know, all the activities, work on it as a group. Well, work on it individually, but pass in your answer as a group. Now I'm going to do something a little bit different than previous weeks. I'm not going to put the answer up. You know, I'm not going to put my solution up until I receive you know, a submission from each table. Then once I receive a submission from each table, I'll check it off. You know, everybody will get credit, and then I'll post it. Okay, because I don't, where this requires a little bit more thought, I don't want to post my answer because, you know, someone could just kind of leapfrog and go right to the answer. And I want to give you enough of an opportunity to see if you can figure it out yourself. Okay? All right, but that's the lecture. So the rest of the time is yours to work on the activity.